right, up next, I want to introduce you to Dan Robinson and Oleg Andreev. They are the product architects at Chain, and they are going to give us the exclusive unveiling of their new smart contracts language, Ivy, for the debut here at the Smart Contracts Symposium. So Dan and Oleg.
Hello. And so, first of all, I'd like to thank Chamber of Digital Commerce for having us here. It's exciting times, and we're really excited to present our new programming language for smart contracts. So I'd like to start with a brief introduction of smart contracts in the context of what we're working in Chain. We're designing the blockchain protocol and enterprise software that implements it. And then I will hand it over to Dan to talk about the Ivy, the language that we work on. So what is the smart contract? As Nick already had a talk earlier today, smart contract is a term that was proposed by Nick Szabo to explain the contractual clauses that can be automatically enforced in software and hardware. And the canonical example is a vending machine, where you can put coins in and get the product out. And the vending machine implements a contract with the bearer, but the question is, what makes this machine different from all other machines that follow algorithmic instructions? And it turns out that the vending machine acts on secured property. Vending machine actually exclusively controls the property, and this gives this extra value for the algorithms that control this property. So in this case, we have two scenarios. Either the buyer comes with the money and puts it in, and vending machine dispenses the product and the change, or the owner may have a key access, the key to unlock the lockbox and get the products or cash out of the machine. So it turns out that the smart contract is not just any algorithm, but an algorithm that operates on a secured property. So what about the digital value? So for physical value, we need some sort of logbox. But for digital value, we need some sort of a secure protocol that establishes the ownership. And it turns out, Nick Szabo also introduced this concept of a property club back in the late 90s, I believe. And the idea goes like this. We implement a decentralized protocol for tracking the ownership of titles, and every owner has exclusive control over their own titles. And they run this protocol between themselves to make sure that all the transfers are properly authorized and double spending or like any integrity violations are prohibited on the protocol level. And Bitcoin is a famous implementation of such a property club. And Bitcoin tackles very narrow and very difficult problem of creating digital currency. And at Chain, we create a protocol that tries to complement Bitcoin and cover all imaginable sorts of digital assets, like in the wide spectrum, from bank-issued financial instruments to simpler things like movie tickets or gift cards. So what is the place of smart contracts in the Chain protocol? So Chain is defined by two parts: the protocol itself, which is a multi-asset blockchain based on based around the federated consensus of parties forming the network. We define the Chain virtual machine that runs on the bytecode to execute the programs that define authorization rules for issuance and transfer of assets. And the Chain protocol is open standard. The second half is Chain Core, which is an enterprise software that implements Chain protocol, verifies the blockchain, but also manages keys and other private user data. And we also open source and let everyone play with the developer edition of this software. So in Chain blockchain, if we zoom in, we have multi-input, multi-output transactions that define the transfer and flow of value. But the value is also annotated with control programs that define the rules to unlock the value and move it to the other transaction. And here we see that outputs have the programs and the inputs have some arguments to these programs. So the transactions are authorized by taking the program, taking the arguments, placing them inside the Chain virtual machine, evaluating it, and Chain virtual machine just approves or disapproves the transaction. And Chain protocol already implements the bytecode, and operation defines exact deterministic behavior of this virtual machine. And this context is pretty rich. We can define the rules based on public key cryptography, like the transaction must be signed by someone, or based on time, or require a payment in some other output in the transaction. And however the bytecode is rich and allows these things, it's a pretty low-level language. And so we need a higher-level language that makes it easier and safer to write those programs. And here, Dan will talk more about Ivy, the language that we work in.
Yeah, so thanks, Oleg. So what's Ivy? Ivy is a high-level language for secured property. And so when we use this phrase secured property, I used to be a securities lawyer here at Paul Weiss here in New York. And secured property, secured transactions in the legal context means something different from what it means. I'm now sort of a cryptographer, and that's what it means in that context. So this is a bit of a pun. It's an extraordinarily lame pun, as one might expect a punner in the area of commercial law to be. But nevertheless, it's the point I'm trying to make here is that Ivy is made specifically for writing a kind of smart contract that depends on certain property having a security interest in this property, such as, for example, putting a mortgage on a house or writing a covered call option, where property that's on the blockchain is secured in this particular way that different parties can retrieve it using different methods that are based on their potential interest in the property. So we're going to power through a few hello world examples of this, and I don't want people who aren't technical to zone out through this, because a lot of the goal of Ivy is to work toward a language that can both be a domain-specific language for writing contracts and financial agreements at a high level that is understandable by lawyers and financial professionals, as well as a language that pretty closely maps onto what's happening on the blockchain. So here's the simplest version of a control program, and that's an account. That represents assets that are held outright by one party. So in this case, all that this program does is check that a signature is provided by a particular public key on the transaction that's attempting to spend the property. So this would be just, for example, my own bank account, my very low bank account that could have, when I spend money out of it, all I have to do is sign a transaction. I don't have to fulfill any other requirements. And here's an example of that program in Ivy. So there's three parts generally of an Ivy program. So first, this specifies the parameters of the program. So the account program takes one parameter, that's a public key, and this is Alice's public key this is embedded in the control program on the output. And for her to spend this $50, she needs to provide a signature using this public key on the transaction that's spending it. Every control program also has one or more paths. This only has one path, and that's to spend the asset using a signature that's on the transaction. And so when she attempts to withdraw this money and spend it, she provides a signature on the transaction. And this is a statement, and you can include one or more conditions that must be met by the transaction attempting to spend the output. And this just checks the signature of the digital signature from Alice's public key on the message. And so if people aren't familiar with how digital signatures work, there's a pair of public keys and private keys that that a person can generate, and they provide that public key to the world and keep the private key secret. And there's an algorithm that you use with your private key to sign a message, and that can be, in this case, for example, the hash of the transaction that you're spending. So you're essentially signing permission to spend this asset in this particular way. And anyone with the public key can verify that you signed this message. So this is a way to store value on the chain in a way that only you can access it. So let's look at a slightly more complex example. This is an offer. As anyone who went to law school knows, an offer isn't actually technically a full contract. But in this case, the idea here is that this 100 euros, if Bob is offering 100 euros, is locked up by this program, and anybody who sends $107 to Bob is able to retrieve this money. So this is a lot like a vending machine. This is property that's put out there in the open on the blockchain for anybody who wants to purchase, as long as they pay the asking price. And Bob, of course, can cancel this offer before it's been accepted and essentially revoke this offer. And so here's our offer written in Ivy. And so you see here, when Bob creates this offer, he specifies his key, his public key, and the price that he expects for the asset. So in this case, it's 107, and the currency that he expects. So in this case, it's dollars. So if you see here, those are the parameters that are provided to the contract. And there's two ways for this offer to be, for the property that is locked by this offer, the 100 euros, to be recovered. First, the transaction can simply include a payment to Bob's account. And so here, this just checks that the transaction that's being spent makes a payment to that account. And the other possible path, and these are mutually exclusive paths, is only one of these has to be satisfied to spend the asset, would be a cancellation. And this just checks that Bob has authorized the cancellation. So this is a very simple way of implementing bids and offers on a blockchain. So as our final example, let's talk about a call option. And this is an American-style covered call option where Bob writes Alice a call option, let's say, for 100 shares of Microsoft. And a call option, for those who don't know, is a contract in which the holder of the option has the right to purchase the underlying asset at a particular price within a particular time period. And so what this means is that there's two ways for the Microsoft shares to be recovered. First, if it happens before the deadline, Alice can unlock the shares, and just Alice in this case, not anyone else, because this is something that was sold by Bob to Alice in exchange for a premium. So Alice is able to unlock the shares by sending a payment to Bob, and after the deadline, if Alice has not yet unlocked those shares and recovered those assets, Bob is able to unlock those shares using his key. And so here's the specification of that call option in Ivy. So there's two paths that can be possible here, and so there's two ways for this to be recovered. As I said, if it's before the expiration date, and so this checks on the transaction that the time of the transaction is before, and that's enforced by the blockchain, by the consensus protocol, then the holder of the option, which is Alice, who paid Bob for the option, is able to use her private key to sign this. And the third condition there is that she has to pay the strike price to the holder of the account, and that this essentially represents exercising the option at some point before that date in June 2017 and paying the strike price in order to unlock these assets and receive them. Then Alice can pay those to whatever address she wants. And the other path that can be taken is to terminate the option. That can only happen, as we said, after the expiration date. And after that point, Bob is free to cancel, to recover the asset that he put essentially in escrow to be sold as part of this call option. So these are some very simple examples. I want to point out one more thing about this call option. So this is a pseudocode call option that was written in 2002 by Nick Szabo in another paper, A Formal Language for Analyzing Contracts. And there's a lot of parallels between how this specification of the call option in Ivy works and this one. And I think that's not an accident, in part because we were influenced by a lot of Nick's ideas, but also because the goal of writing this contract in the way that we've designed our smart contracts and transactions is to try to be a domain-specific language that lawyers can understand. And that was the goal, Nick's goal, as I understand it, with the paper. It's not just to be for programmers to write programs that can run on a blockchain or decentralized applications. It's for lawyers to be able to say, this unambiguously is what's supposed to happen in this series of events. So I don't think we're necessarily quite there where lawyers are going to be poring over these instead of offering documents. But the hope ultimately is that this is something that a lawyer would be able to review, because this does reflect, to some extent, just a formal expression of the same logic that's represented in those contracts. So in summary, Ivy, it's a declarative language. And what I mean by that is that, as you see here, all the statements are just verifying that a particular expression is true, or that a particular condition holds. And one nice thing about that is that people talk a lot about formal verification, which we think is a very important part of smart contract design. And essentially, to really oversimplify, what formal verification is you list a set of conditions that need to be satisfied by a program, and by a program that you've written, and a checker makes sure that the program fits those conditions. That, for example, if there's a transfer between accounts, one person's account only goes down by the amount that the other person's account went up. So that can catch a lot of bugs in programs. instead of writing programs imperatively and then checking them with a declarative language, we've just written Ivy as a declarative language. So all you do is you specify these are the conditions that must hold. This is what must have happened. These are the conditions that must be done before this money can be spent. And so we think there's still room for improving this language of security and making sure that all these assets are accounted for. And there's still possible ways to write bugs in it, but a whole class of bugs is impossible. And you essentially get a lot of the features of a formal verifier for free. This is a predicate language. So as you see here, all this does is it's a list of verify statements. And this is either going to succeed or fail. So it doesn't compute some new value. And we think that's useful in part because it matches the infrastructure of how our blockchains work, where state is an immutable object on the blockchain. You don't try to just change objects on the chain, and you don't have a lot of computation done by nodes. We also think it really matches often how contracts work, where really what you're trying to figure out is whether what happened was authorized under the terms of the contract and the law. And so you can use Ivy programs. You can write this and use these programs to govern the transfer of assets and to create assets that can be transferred in particular ways. It can be offers that can be lifted, options that can be exercised. And you can also use it to write programs that define the issuance of assets in the chain protocol. So there's ways to design custom assets that can be issued only by a group or a consortium, or assets that can be only issued in exchange for another asset. And so that's something, if you have questions about that, look more. We can talk to you about some more about the chain protocol and what that means and how assets work in chain. And finally, in addition to compiling to the chain VM, we also have a version of Ivy that compiles to Bitcoin script. So Bitcoin has, I don't know if this has been mentioned today, but there's a smart contract language built in to Bitcoin. And it's a relatively simple one. It doesn't allow necessarily particularly sophisticated applications yet, but it can do a surprising amount, particularly in the area of authorization of transactions. So particular complex, say in 5 of 4 of these particular parties, 5 of 6 of these particular parties, and then 4 of these other 9 need to approve of a transaction. And we find that Ivy is useful for some of those use cases and also other more sophisticated sort of ingenious uses that some people have found for writing programs in Bitcoin script. And we think Ivy makes those programs a little easier to read and to write oneself. So to learn more, you can download Chain Core. That's our enterprise software. There's a developer edition that's available at chain.com. If you are interested in learning more about Ivy or about our protocol or virtual machine, you can go to chain.com/docs, and there's a tutorial on Ivy there now that you can check out. Ivy is still a language in research and development, so if you want to work on it, if you want to try out what kind of programs you can write in it and what applications can be done, then I'd encourage you to talk to us afterward. And so we've also got 2 people here from Chain, Jill Carlson from our business development team, and Tess Rainerson, who's on our systems engineering team. And we'd be really happy to discuss more about what Chain does and how it can possibly help you. But enough of talking my book there. The meetup, finally, we have a meetup tomorrow at 6 p.m. That's right here or in a nearby room. And so we'd encourage you to sign up. We're going to be doing a presentation on Ivy and getting a little more into the technical details and what can potentially be done with it. And we're also giving a talk on how our database system works and our high availability solution for databases. So if any of you are systems engineers, we'd really encourage you to come see that as well. So you can sign up for that meetup. That's tomorrow at 6 p.m. here at Microsoft at meetup.chain.com/NYC. So thanks, everyone. It was really an honor to speak here. And thanks again to the Chamber of Digital Commerce for having us. And we've really enjoyed being able to present this here.